Okay, so the first thing I want to do, just really quickly, is just check your homework. I'm not going to grade it. I just want to see that you did it. It was, what letters was it? J and K?
Yeah, JK.
Yeah, JK.
Oh yeah, it was.
Because I remember when I realized, like, oh, I gave them J and K as in, you have homework JK. I hope nobody interpreted it that way, like, just kidding.
See, Andre, that can be your excuse for not doing it.
It won't fly, but we can try. I didn't mean to rhyme.
Fly it or try.
You have to do half of J and nothing on J.
I didn't hold an accomplice in the
That's not a good enough.
I should do it, but then I gave
You weren't?
I gave up
Okay.
in instant.
I can't remember. Was it just
you can see
Evan?
the
You were
dots
obviously
on the
gone Thursday. Trevor, you were gone. I don't think anyone
It's
else
not
was gone.
good. I just got through here and that's all I could do. I was so mad. But then I realized I had like I had to get my Okay. Don't look.
Why?
Don't be mad.
Yeah,
I got
don't be
dots
mad.
on one graph and that's all I could do because I got mad.
What?
I got down someone around as well.
I was confused and I had lost stuff and I was tired.
When did you try? When did you do this?
Last night.
Oh my god! As soon as you said tired, I was like, I probably know when that happened.
I'll be real with you.
I completely forgot about it.
I didn't forget about it. I just totally did that because I couldn't remember.
Guys, I was trying to give you easy points.
I was like, it doesn't go like that, so give us easy points.
Oh my gosh.
Anybody can quit. I did. Hey, I did part of it.
Okay.
I did part of it.
So did I. I did a graph.
10 minutes after this class, it never went through my line again.
Well, I would have done it in ish on Thursday, but it was Thursday. But we had to get through that knowledge assessment. So, and then I had to finish that last night. I didn't even get done. I got my English up to 70, but not my math. It's making me do 20 minutes worth of notes.
Oh, no.
It'll heal and then go straight. Because if I was so I was ready to be done, so I just started clicking skip, and it counted all of those wrong, like I didn't know. So I got 50. And so I have to get those 12 points back, and I'm gonna just and it has to be done by tomorrow.
This was supposed to be gimme points.
Because Seth wasn't there.
Huh? That's not why.
I don't know what to do.
We know why, but
I was just going to do like 10 points completion.
Give us all zeros.
This has been a practice drill of your preparedness, of your effort and skill.
I feel like
1 point.
I tried, but I just couldn't pull it off. Because I did attempt at a graph.
Alright, I'm going to give you guys a free pass for this one. Yeah, we're going to go over it. Again, virtual students, if you haven't turned yours in either, I'll do the same thing, do a free pass. I just need it turned in, at least at some point. So I'm going to go over it with you guys, and you all need to do it with me, and I'll give you points for that homework. Virtual students, if you follow along with me, finish it and then submit it. Even if it says it's late, I'll still count it and give you full points. Yeah, I'll do it that way. Another virtual students, I really hope that you guys are following along. I know it's only you two. My engineering virtual class is doing terribly. I had 5 out of 17 kids turn in anything. And they've had like 5 different assignments that were all due. And so I have like 10 kids that are missing 2 weeks worth of work. So they have straight up zeros.
Sadly,
So I'm really concerned.
I took a semester of that class last year, and that's about the type of students.
That is
I mean,
It's
I did all my work, but like last year, like
Intro to Engineering Design.
I took a semester of it.
Yeah. It's not a
It's
joke
not
class.
part of a class, but no.
Well,
there's just people
yeah.
that didn't want to do it.
Yes, and that has been the experience. So virtual students, please stay up on your work. I know for this class we haven't had a lot of homework. I really hope you've been following along with all the class recordings, all the topics we've talked about, following along with us going through all those sheets, looking at different aspects. We're getting close to wrapping up this unit, wrapping up kinematics. We'll look at some free fall motion, which is kind of what you guys did. We'll look at projectile motion. It's like if you shoot a cannonball through the air, we're going to look at that motion. And then we're going to finish with kind of the key equations that we use. We're going to formally summarize them. We'll probably practice a little in review and then have like a test on just this unit for kinematics. So it's coming up soon. I don't know if that'll be end of this week or maybe beginning of next week, but we're getting close. So I just wanted to mention that. Okay, let me get the projector up. We will do your guys' homework. Sorry, I'm cutting you off. Okay. So we were on J, weren't we? Okay, so right here, this scenario, we're looking at free fall, right? Assignment 1J. Evan, I'm sorry, I need to get you in. We're on this. That was like what I assigned this homework. All right. So everyone, this is where we're at. We're doing a acceleration time graph. So we're plotting this rocket's acceleration over time. All right, straightforward. It told us the rocket starts from rest and fires straight up. That acceleration is 5 meters per second squared for 10 seconds. So if I plot the acceleration for 10 seconds, what's my plot going to look like if it told me it's 5 for 10? Straight line. It started from rest and immediately was 5 meters per second per second. So when you draw this, just draw the line straight across. That's all it is. It wasn't a trick question. You're on J. Yeah. Right? It told us the acceleration happened for 10 seconds. It gave us the quantity. So when we plot what was the acceleration for any moment of time, it was the same acceleration for the entire time. So literally just draw this line straight across at 5 meters per second. right? What we would draw is Does that make sense? The acceleration over time was exactly 5 meters per second the entire way. It was constant acceleration. So that one's easy. Sketch a graph of the velocity versus time. What did the velocity look like? Well, it said it started from rest, right? So at 0, I have no velocity. Right? It started from rest. If I accelerated at 5 meters per second squared, after 1 second, how much did my velocity go up? 5, right? Does that make sense?
Yeah.
If I'm accelerating 5 meters per second squared, that means my velocity is increasing by 5 meters per second every second. After 1 second, my velocity is increased 5 meters per second. So now I'm up to 5 meters per second. At 2, I'm going to increase another 5 meters per second. Now I'm up to 10. You can see the pattern. Every 2 seconds, you increase 10 meters per second. Because every 1 second, you increase 5 meters per second. Right? Does that make sense? I just look at any moment in time, what's my velocity? Well, every 2 seconds, it goes up by 10. 10, 20, 30, 40, 50. I've now plotted this rocket's velocity over time for the first 10 seconds of its motion, which is just it accelerating straight up from rest. Right? What should the slope of this line be?
Should be 5, right?
Should be 5. Ethan, why do you say it should be 5?
Because that's the acceleration.
Yeah. And what is the slope of a velocity time graph? What does it tell you?
Acceleration.
Yeah. The slope of a line is rise over run. How does y change as x changes? Well, if it changes by meters per second every second, well, meters per second divided by second, that's an acceleration. So that's exactly right. This slope should be 5. Obviously, if it goes up by 10 in 2 seconds, 10 divided by 2 is 5. 5 meters per second per second. Now this first question, determine velocity of the rocket after the initial 10 seconds of travel. Well, that's easy. We literally just plotted it. After 10 seconds, what's the velocity? Just reading straight off the graph.
50 meters per second.
Bam. 50 meters per second. That's easy. No, because it asks us the velocity. So it said, what was the velocity after those 10 seconds? It was traveling at 50 meters per second. Now, this is the big question. From the graph, the velocity time graph, determine the height of the rocket after those 10 seconds. Huh? I didn't quite get that.
250.
I got 250. How do we do that? All I have is velocity versus time. I don't have position versus time. I can't just look up, oh, it went, 200 meters at 10 seconds. That's how high it got. How do I do that? Huh? Yeah. So, Evan, this was kind of a big breakaway that we found. If you calculate the area underneath a curve, specifically a velocity time graph, when you calculate an area, you take length times width, right? So what's the width of this triangle from here to here. 10 seconds, right? So I have 10 seconds. My height is what? 50 meters per second. Is this the right calculation for the area under this curve? It's a triangle. This is a rectangle. This rectangle would be length times width. I need the 1/2 because it's a triangle. Yep. So Evan, we found when you do this math, right, 500 divided by 2, you got to check your units. I'm taking meters per second, multiplying by seconds. So I really have meters per second times seconds. Well, those cancel. The area under the curve is a distance. It's just meters. We measure displacement in meters. So what we found is when you take the area under the curve of a velocity time graph, just calculate the area, you actually get the displacement of that object over that entire period of motion. You could do the same thing at 5 seconds. It's just going to be this area. The answer is the same. It's the displacement of that object during that time period. Right? So we can find out the height of that rocket is 250 meters. Because we found the displacement from start to end. It displaced 250 meters. The other key thing, and Trevor also, when we had a line that went into the negative and went below the horizontal axis, that's a negative area, right? So if my graph, I want to make this up. Say it looks something like this, right? This is now the negative. So this area is negative. This area is positive. This is negative displacement, that's positive. To find the total from start to finish, I just add those areas. If it's negative, that means overall, I started here and I displaced in a negative direction. If the total ends up being positive, that means I started here, I may have went backwards, but then I finished ahead of where I started. Alright? So that was, again, that displacement. Make a claim about the value of the acceleration at 10.1 seconds. So this I was challenging a bit because we hadn't even talked about this. So it accelerated for 10 seconds at 5 meters per second upward. Well, then the engine just cut right at 10 seconds. What did you guys say the acceleration was at 10.1 seconds? Like a moment after the engine cut. What was its acceleration? Huh? I got a 0. Slightly less than 5. Well, we use math in this class.
Or it'd be negative.
Or is it negative? Remember, it's the acceleration.
It's still moving upwards.
Yep. Your motion and acceleration don't have to match.
Because it could still be moving upward, but not have acceleration.
Well, let me ask you another thing. When it was shooting upward, that rocket was accelerating it. The rocket was the force acting on it. And in total, it produced 5 meters per second, of acceleration upward. When that rocket cuts out, if there is no acceleration, it would continue at 50 meters per second. No acceleration, it'd just stay at 50 meters per second forever.
So it's negative.
It is negative, which makes sense. If I launch a rocket and then cut the engine at the top, it doesn't just keep going at a steady velocity. What does it do? It starts to fall, right? It peters out, and then it starts to come back down.
I think we have to shoot a rocket.
That would be sweet. I wish I had stomp rockets. Anybody have stomp rockets as a kid?
Oh, yeah.
Yeah, I had one of those and I loved it. It's like a little airbag with a hose, and it has like a plastic nozzle, and you just put a plastic rocket on it, and you literally stomp on this thing, and it launches the rocket. All the air pressure shoots the rocket straight up. It goes like 50 feet in the air. That would have been sweet. Aiden?
We had one as a kid. I can't remember how we got it, but me and my brother, we set it up. And the first time we both stomped on it together and just broke the thing.
Did you really?
We only used it once and we broke it.
That's depressing. Yeah, anyway, that's exactly right. Engines cut. It keeps going for a little bit and eventually stalls out, right? And it starts coming back down. Why does it come back down? Gravity. If there's nothing acting on an object in the air, doesn't it just start falling down?
Wait. Technically, according to Thursday, his answer would be incorrect. He didn't explain. He said because gravity. So explain, Ethan. Gravity is a constant force pushing every object to the center of the air.
That is correct.
There you go.
Yes. So really, let's reassess. You launch it for 10 seconds, the rocket accelerated, and then the engine's cut. What's its acceleration like the moment after it cuts? We just said that gravity's acting on it. That's the only thing that's doing anything to the rocket. Do you guys remember the magic number for gravity? No, that'd be an unreal gravity.
Someone else you got some negative. Who was you? You was who?
Okay. Maggie, some for the newspaper.
Registering the
Are you helping them, or are they like interviewing you or something? Okay. I don't know if they just have a question or if they're having you go help.
Wait, who wants their picture?
So yes, it's just gravity. What's the magic number for gravity? Do you guys come across it? The negative number.
Negative.
No.
40.
Something with an apple.
Seriously, no one knows it?
3.
Hold on.
Negative 0.
It's 9.8.
Yes, thank you.
Okay.
I thought that would ring a bell,
I knew
right?
I knew it was.
You looked it
Okay,
I looked it up.
Google.
I knew it was.
Hey Siri.
Wow, you're so smart. You looked it up, Ethan.
Should we invalidate his answer since he used his phone in
Yes.
class?
I know I did. It's over there.
Wow, you're rough on your phone. 9.8. Now, again, I'm not expecting you guys to know this. Part of this was a challenge. We didn't talk about this, so I didn't expect you guys to know this. I wanted you to give your best shot. That's what the acceleration is. The reason is as soon as if it's just an object in like free fall, means you just threw it up there, meaning the engine's cut out, right? Nothing's happening. Gravity's the only thing doing anything to it. Any object in the air, if gravity's the only thing acting on it, that's the acceleration all the time. Now, a lot of times, I might tell you, do -10. Especially on like a quiz or something. Especially like if I don't want you to use a calculator, I'll just say do 10. Because then your math's easy. You just have 10. But anyway, that is the acceleration the moment after the engine's cut out. Because all you have is gravity. Why did I say it's negative? Yes. We said this is the y direction, or x, it doesn't matter. This, we started at 0, and we went up. We went up to a height of, what was it, 250 meters? This is positive direction. Acceleration's a vector. It has a value and a direction. Was it just a question, or?
Yeah.
Okay.
Yeah.
What were they questioning?
The negative direction, if it's accelerating downwards, that's a negative acceleration. So that's why I say negative. Because it's changing the velocity in the negative direction. All right? How do we kind of did this. Explain your reasoning for what we just answered. Why did we say it was 9.8 or 10? What's the reasoning? Yeah. Right here, our reasoning would be there's nothing else affecting the rocket besides gravity. Really, our evidence would be like, it is scientifically agreed that acceleration of Earth's gravity is 9.8 meters per second squared. So you can cite that as a scientific fact, or at least scientific agreement as your reason. That's all it is. Do 9.8. Negative 9.8 is it's actually like negative 9.81 something, I can't remember. But.
That's what you put for the 0.1 seconds after the
Yes, right here,
You put negative 9.8.
9.81 meters per second squared. Because we just talked about that. That's just gravity's acceleration. Our explanation is not the greatest, but it's basically gravity's the only thing doing anything to the rocket, and it's a scientific agreement that it's Earth's gravity is negative 9.8. Now, we already talked about this. Oops. Oh, we didn't. Oh, that's a good question. I want you guys to really think about it. The moment after the engine's cut out, we said gravity is acting, and it is decelerating. The acceleration is negative 9.8 meters per second squared. But look at the motion. Is the rocket still moving up, or is it moving downward right after the engine's cut?
Still moving.
Any other thoughts? It is still moving up. Do we get why? Do we understand why? The other thing, yes. We were increasing our speed over and over and over. We got to 50 meters per second. As soon as we cut the engines, it's still going to be moving 50 meters per second, but now gravity's going to slow it down, eventually hit 0, and then it'll start coming down. The other way to think about it is the moment after the rocket engine's cut out, can you go from positive 50 meters per second to even negative 1 meter per second in a tenth of a second? Yeah, that'd be insane, right? Your acceleration would be basically 50 meters per second divided by 0.1 seconds to get back to even 0 meters, that standstill. Wouldn't that be 500? I'm not super great at mental math. This would be like 500 meters per second. Your velocity would change by 500 meters per second every single second that passes. That's not even close to what happens. Yeah, that's absurd. That's unreal.
Wait, what if it's like a real rocket?
I don't know what they actually launch at.
Well, I mean, I know they don't launch automatically like that, but they do build up speeds.
Google. I do know. So again, I'm really into cars. You know, Top Fuel dragsters. The ones with the huge rear wheels and then the teeny tiny front wheels.
Yeah.
Those accelerate at like 3 Gs. So like 20 meters per second squared. They go like 0 to 100 mile an hour in like 0.8 seconds.
The speed of sound is 343 meters.
Yeah.
So you'd be accelerating faster, almost twice as fast as you get.
I hope this plays the actual video. No, this is it. I want it to play the full speed run. Yeah, there it goes. So they're already at like 100 mile an hour, 200. But this is slow motion. To accelerate that fast, you need crazy forces. Like these engines have like 8,000 horsepower. Your minivan has like 150, 200. If you have a car that has 1,000 horsepower, you probably spent $100,000 to buy it. Yeah. At least.
Well,
look at how much the tires wrinkle. They twist so hard to launch it that fast. Yeah.
Well, and then
They're
also with
insane.
those, because of how hard they use the engine, don't they have to replace them fairly?
They tear the engine down and rebuild it every run.
Okay, that's what I thought. I was just making sure.
Yep, and they can do it in like 30 minutes.
That's
So they do one run, like a quarter mile. They do the quarter mile in like 4 seconds, 5 seconds. A normal like Ferrari can do it in like 12, maybe 11 seconds.
Are those legal on the...
No. Not even close. These are the top fuel. That's like the highest class. This is like
How much should one of those cost?
probably millions.
Millions.
Yeah. They're insane. But anyway, it's a nice tangent, but
So when you're going that fast, you can't even steer it. It's like a roller coaster.
they
You
do.
die.
They literally react because sometimes it'll land and pull them off, and they have to it's.
But you have to
It's
be,
a whole
very,
new-
very, very light on your.
Yeah, if you were to,
rip it, you're just
hard-
gonna die.
Yeah, they're pretty dangerous. But anyway, all that to say, if your rocket, it goes up, it hits 50 meters per second, the engine's cut. After 0.1 second to get it to come down, you would have to accelerate or decelerate an insane amount.
Double the speed.
So that you know, after that 0.1 second, the rocket is slowed down a little bit, but it's still going up. Right? Even after 1 second, the engine's cut at 10 seconds. Another second passes. If it started at 50 meters per second, and we say we have a deceleration of negative 10 meters per second squared, how fast is it going after 1 second? It was going 50 meters per second, and then I cut the engines. Gravity is the only acceleration. It'd be 40. Because gravity is decelerating this way. It decreases my velocity. So then after 5 seconds, then I hit my standstill. Because it's gone down by 10 meters per second every second. So at 15 seconds, I'm at that standstill. If I go another second, now I'm starting to come down. Now I'm going negative 10 meters per second. And it keeps increasing by 10 for every second that passes. True. We don't consider drag all that often. That gets super complicated. But a lot of times if we do, you'll be given like a generic force for it and then include it. All right? Does that one make sense? I think the next one is almost the same. Yep. Launches, it's the same situation. It goes up at 5 meters per second squared, just like the last scenario. That happens for 10 seconds. Then you cut the engines. Draw the acceleration time graph. Hey, John, are you with us? So, what we're doing, let's do from 1 to 10. It's the exact same graph that we drew before, right? How did I scale this? Oh yeah, by 2s. Right? From 0 to 10 seconds, just like the previous scenario. My acceleration was 5. That should make sense. For 10 seconds, that rocket's shooting up at 5 meters per second squared. It's the same acceleration for the whole 10 seconds. Again, this is acceleration versus time. What happens the moment I turn the rockets off?
You plummet to -10.
Yes, the acceleration instantly changes. How do I do this? -2. So the way you do that, I'm drawing down here. A lot of times you can draw like a dotted line. Technically, it's a transition, right? You'd cut your engines, and they'd still be sputtering a little. So your acceleration, it goes down, it hits 0, and then gravity starts to take effect. But we simplify things, so we're going to imagine that it instantaneously switches. So I draw this dotted line to show it jumps from here to here immediately. And then what happens the last 10 seconds?
You're holding that -10.
Yes, gravity's acceleration doesn't change. This guy's just falling. Oof.
Low release.
Okay. Now let's look at velocity versus time. I'm going to draw it over here. There's a reason why. So when I start, blow this up. There. When I launch my rocket, I'm at 0 meters per second, aren't I? I'm starting from rest. I'm starting on the ground. I don't have any velocity when I start. Remember, it accelerated at 5 meters per second squared. So every second that passed, I go up 5 meters per second. How did I topped out at 50. So after 1 second, I'm at 5. 2 seconds, I'm at 10. Does that make sense? Every second, my velocity increases by 5. Every second, up by 5. Every second, up by 5. Right? Eventually, after 10 seconds, I'm at my max upward velocity was 50 meters per second. Then I cut my engines. How fast am I going 0.1 seconds after it? That's acceleration. We're plotting how fast am I going?
1 second after or 0.1?
Like 0.1. Approximately how fast am I going?
Very close to 50.
But more or less than 50.
Less.
Less. At this point, my engine's cut. I'm not increasing my speed. Gravity is actually slowing me down and decreasing my speed because the acceleration is now in the negative direction. So right here, it's something like this. Now I just put a temporary point. After 1 second, what's my velocity? I reach 50 meters per second, then I cut the engines, and gravity's doing its thing.
40.
It's 40. We're going to use 10 for gravity's acceleration. Gravity's acceleration is negative 10 meters per second squared. In this case, it's decreasing my velocity by 10 meters per second every single second. So at 11 seconds, I'm actually at 40. After 1 more second, what's my velocity?
30.
Boom, 30.
I'm going to double the speed.
Does that make sense?
And technically, this looks like a real experiment. You would be gaining more speed and going faster at longer
Yes, and we see that. Because right here, it's in free fall. You get it up there with the rocks, then you just cut it. It's basically like you drop it.
Yeah, but as it falls, it's going to be picking up speed.
Right, it's acceleration. Its velocity is going to be going down.
Yes, it's picking up speed. However, this part, this segment, it's actually losing speed.
Yeah, I'm saying it's picking up speed in a negative direction. So I guess.
Yes.
Yeah.
So this is tricky. When we were going up, we had positive acceleration. The acceleration and the velocity were in the same direction. That means you're increasing that velocity, right? So at this point, we have positive 50 meters per second. Well, then we switch, and now I'm decelerating this way. So every second, my velocity's increasing in this direction. Well, increasing in the negative direction is actually decreasing because we said this is positive. So technically, it's not gaining any speed because the velocity is decreasing. But you can think about it as increasing speed in the negative direction. But you might not want to think about it that way because you want to think about what's happening physically. Well, it's slowing down. It's kind of petering out. What happens right here? Why is that important? This point.
Because you stop moving.
My velocity at that point is 0. That's my apex. It goes up, and then it starts slowing down. Then it stops for a split second.
And that is 15 seconds.
Yeah, 15 seconds.
And then you would start going back.
And I start to fall back down. Now I'm increasing my velocity, but it's in the negative direction. The value is getting bigger, but it's because it's going this way. That acceleration is exactly the same. After every second, it goes up by 10. I think it's like that. Right? Does that make sense? I'm going up, increasing. My rocket is increasing my speed at 5 meters per second every second. Then I shut them off, and gravity is the only thing affecting me. Well, it starts decreasing my speed at 10 meters per second every second. Eventually, I get a standstill. I've reached the height. Now I'm going to start to go downward. So my velocity now increases in the downward direction. I get faster and faster and faster going down. Right? I'm going to leave those up. We're going to try and just read through this. This is saying you use this kinematics equation. This is a known equation. If I try to solve it with my motion, why is my math wrong? On the back side of that sheet, if I want to know my position, I got to put in my initial position, my initial velocity, the time that I'm looking for, the acceleration, and the time again. Why is this answer wrong if it's trying to figure out to find when the rocket lands back on Earth? So I want to find when does it get to 0. If it starts at 0, initially it goes up 0, and it goes at 5 meters per second squared for a certain amount of time until it gets back to 0. Why is that calculation wrong? Does everybody see the mistake? Okay, the initial position, that's at 0. It starts on the ground. The initial velocity was 0. It started from rest. We're trying to find the time. Is the initial, or the acceleration correct? Was it 5 meters per second squared from rest until it came back to the ground?
Oh,
No. This is not accurate. That is not the acceleration of this object from when it left the ground until it came back. It was not a constant 5. It was 5 for half of it, and then the acceleration switched when you turned those rockets off. So if we try to use this calculation, we can't just plug and chug. You'd have to do 2 parts because you have 2 accelerations. All right? So that one is just, the acceleration is not 5 meters per second for the whole time. Now find the time when the rocket reaches its maximum height. We did that. Right? Like that. This is the maximum height. Right? It was going up and up and up. You turn the engines off, and gravity started to slow it down. And as soon as you hit 0, then the rocket's going to start pulling it back down. How can you make sense of that in terms of displacement? Remember, displacement is the area under the curve for a velocity time graph. How can we use this explanation, this idea of area under the curve, to figure out its maximum height?
would you just take the positive value?
Why would you? What's the positive value?
Like everything before it starts going back down.
You want all this?
Yeah.
Why would I only take that?
Because when it starts going back down is when you start subtracting back to 0.
Yeah. If I were to do the whole motion, I want the displacement. Well, if I go start to finish, I got to take positive displacement minus negative displacement. It's across the horizontal axis. The result of that tells me from start to finish, what height am I at? So I take all my positive displacement, and I have to actually subtract how much it displaced in the negative direction. And then wherever it's at, right? So that last question, you could use that answer. How did you determine the max height? What is the rocket's maximum height? It's not here, right? Where does its maximum height occur? Ethan, you kind of already said it. Yeah. From here to here, that rocket's moving in the upward direction. As soon as it crosses this line, it's now got a negative acceleration. It starts to come back down. So when you look at part D was the time, the last part is calculate it. Well, how do I do that? I'm going to just take the area under the curve, but I got 2 triangles. I'm going to get A1 and A2, and I'm going to add them up. Right? The area under the curve, velocity time, gives you displacement. I want only positive displacement to figure out how high did it go, what's its max height. So I just do this triangle plus this triangle. Just do my area.
We already did the first one.
Add the 2, yep. I think I got 375. So you take the 250 we already did, and then you add this triangle. Any questions? Does that make sense? I think it's 375. That makes sense. I'm going to wait on that stuff. Evan? Yes, real quick. I want to at least show you this. You guys have heard of PhET simulations, right? Have you done them in any other classes? So it's from Colorado University. They've made a bunch of simulations for different aspects of science. I want to at least show you this one. You don't have to do anything with it. I just want to show you. It's going to show you the actual motion, and then it's going to plot position, velocity, and acceleration. And I want to do one example and look at, okay, for the same motion, what do these look like? So give me some numbers. Where do you want this guy to start? You want him to start right at 0? You want him to start over here? Just give me a number. It doesn't matter. Sorry, I heard -8 first. What do you want his velocity to be?
How much you said?
10.
That's a good question.
Want to do 10? And then why won't it show me my acceleration? Oh. Sorry. The display settings, I think, are cutting off the bottom of it. I just did it earlier today. There we go. So what I have, -8 starting position. What do you want its velocity to be? Did you guys say you want to max it out? How about its acceleration? Do you want him to speed up, to slow down, or to stay constant? Slow down by how much? Jeez. See that? So one, this will show you the vectors. So our velocity vector is 10, our acceleration is -10. When you play this, see how he's slowing down? And then he starts increasing in the negative direction. You see that? That acceleration vector was the same. He had a constant acceleration. It didn't change. That velocity vector did. I was going in the positive direction, but I was accelerating in the negative. So it slows me down and then starts to increase my speed in the negative direction. Obviously, he was showing position. You can also do the same thing. Here, what did we say? -8, 10, and -10, right? So then you can show like an actual plot. See his position, Eventually he slows down and he stops, and then he starts going the other direction. Right? His velocity is constantly decreasing. What would the slope of this line be? 10. The slope of your velocity time graph is the acceleration. That slope is negative 10 because we set the acceleration to negative 10. Right? Does his position make sense? Right? He started off really fast. His position was changing pretty quickly. But then it slowed down, he slowed down, then he stopped. And then he started to speed up in the other direction. He started to go backwards, right? He went like this. You see that? What happens if I say he starts at negative 10? Let me reset. He starts at negative 10 and goes at a velocity of 5 meters per second with no acceleration. What is his position going to look like? Is it going to be a curve? Is it going to be a straight line? Is it going to be like this? What do you guys think? He has no acceleration, so his velocity won't be changing. And his velocity is set at 5 meters per second. Be a straight line like this, you're saying? Something like that? What would this one look like? Would this be a straight line, negative, curve? Plot his velocity over time. If it's set to 5 meters per second and no acceleration, should be a straight line, right? Well, I thought I drew mine exactly. It's close-ish. You see that? His velocity is not changing. There's no acceleration. He's just moving in one direction at the same speed. What is the slope of this line? Position versus time. No. We set this at 5. This at 0. 5. Why did you say 5? How did you know the slope of position time would be the same number as velocity? It's a good guess. Velocity is meters per second, changing distance over time. Well, if I find the slope of distance versus time, I get rise over run. That's distance per time. Oh, yeah. So he hit the wall, so his position's not changing and his velocity's 0. Right? The slope of position time gives you velocity. The slope of velocity time gives you acceleration. Because acceleration is the change in velocity over time, rise over run. Velocity is the change in position over time, rise over run. Right? So I just want to at least show you guys that. That's all I have for you right now. I'm going to wait until we do the next one is actually just a mathematical practice of linearizing data. We'll walk through that one. And then we'll get to projectile motion. And then I have a simulation that I'm going to have you guys do. I think we can get through it tomorrow, or excuse me, Wednesday. But then Thursday we might have to push it till then. Aiden. More than 1 0? Yeah. Behind what? This? Yeah. No. The scale only goes from negative 10 meters to 10 meters.
So you can't put like 1,000 on it?
No. Are you talking about like his velocity? I can try it. I guess I could. How about if I do 1,000 or 100 meters per second? Right? I'll put them at the far left, starting from rest, and we'll say 100 meters per second squared. What was that? In like 0.8 seconds, he traveled 20 meters and slammed into the brick wall. So yeah, that was just, I wanted to show you guys at least how they're made at the same time. It's one piece of motion, but you can plot it's the position, the velocity, and the acceleration. They're all linked. They all describe the same reality, but they all tell you different things. Hi, Allison. What's that? You're the Chelsea. Okay. Perfect. Got your names. Thank you. Now this will be the simulator we'll try and get us ready to use. Found out you can launch cars in it, so that's pretty cool. I think it's pretty sweet. But once we talk about projectile motion, we'll use this to like tinker. We can try predicting. Like that's the goal, is I do the math, and if I'm at this height and I need to hit the ground here, well I know the change in height, I know my initial velocity and my angle. And so you can do all that math and just figure it out, set it if you want, and it'll work. Because this is based on the same equations you guys would use to figure it out. So that's what we'll use that for. But we need to introduce projectile motion, because when you get to projectile motion, you now have two directions. It's not a rocket going up and then down. It's not a car going this way and then this way or just this way. You launch something and it's going up and sideways, doing both at the same time. So that complicates things a little bit, but you can solve it really easily. All right.